Forget the landing, the ride home? That's what actually kills you. Number 10. Communications blackout. The capsule hits thickening air and ionized gas wraps around it like a sheath. Radio waves don't get through plasma. For roughly 6 minutes, mission control at Johnson Space Center loses every voice loop, every data stream, every heartbeat monitor from Orion. And it happens at the worst possible moment, right when heating peaks and every system aboard is under maximum stress. Inside the cabin, Reed Wiseman and his crew run a rehearsed sequence. Short verbal calls, instrument scans, steady breathing. On the ground, the flight dynamics team watches their telemetry screens freeze. The last data point just sits there. They've spent years preparing for this gap, programming every contingency they could model into the onboard computers, and at some point they had to accept something uncomfortable. They've handed full authority to 4 people and a machine. There's nothing left to send. Here's what makes this different from a normal communications dropout. A failure that starts during those 6 minutes grows unchecked. A slow leak, a drifting sensor, a connector working loose under vibration. None of it shows up until the plasma clears and the signal comes back. By then, the problem may have compounded into something nobody can fix. During Apollo, the blackout lasted about 4 minutes. Orion comes in faster and steeper from lunar distance, which stretches the window and raises the stakes. Every other threat on this list plays out inside that gap. Number 9, backshell thermal breakthrough. Everybody focuses on the heat shield. Fair enough, it's the dramatic part, but almost nobody talks about the back of the spacecraft. The conical upper shell of Orion is covered in over 900 silica tiles, cousins of the ceramic tiles that protected the space shuttle. They don't burn away like the heat shield does, they insulate, and right beneath them sits the pressure vessel that holds the crew in the air they breathe. Post-flight data from Artemis I turned up something the thermal models had missed. Radiative heating on the backshell came in significantly higher than predicted. Superheated plasma doesn't just hammer the base of the capsule, it curls around the shoulders and bathes the upper surfaces in radiant energy that the original models never fully accounted for. After the flight, NASA engineers and researchers publishing through the AIAA had to revise entire aeroheating databases to close the gap between what they expected and what actually happened. Because for Artemis II, those corrected models drove changes to tile thickness and gap filler specs across the whole backshell grid. Now, if a tile cracks under thermal cycling, or a gap filler between tiles starts to degrade at peak heating, there's no ablative backup up there. No sacrificial layer burning off to carry heat away. Bare structure. Heat soaks inward toward wiring harnesses, avionics bays, and eventually the cabin wall. The crew has no line of sight to the back shell. They won't feel a tile shift. The only clue would be a temperature reading climbing on an interior sensor. And during the blackout, nobody on the ground can tell them whether that number is real or whether the sensor itself has been corrupted by the same plasma causing the problem. That ties directly back to number 8. Number 8, avionics and sensor damage. Plasma doesn't just block radio, it bathes the vehicle in heat and charged particles that can make instruments lie. A temperature reading drifts high, a connector degrades under thermal stress, a data line picks up noise that looks exactly like real telemetry. Orion's flight computers are built with quadruple redundancy, 4 identical processors that compare outputs and reject whichever one disagrees. When a single sensor fails, the system handles it cleanly. But here's the scenario that worried Lockheed Martin's avionics team. What if the plasma corrupts multiple readings in the same direction? All 4 computers agree on the wrong answer, and then they issue commands based on that wrong answer, making a small problem worse while believing they're fixing it. After Artemis I, so that team ran arc-jet tests specifically to simulate correlated sensor failures. They found that high-energy particles could flip individual bits in memory, It's a phenomenon called single event upsets, and it has been plaguing spacecraft electronics since the early shuttle flights. They hardened connectors, built cross-check routines into the software to flag inconsistent patterns, and gave the crew manual override authority when the numbers looked suspicious. In trade press interviews, Lockheed's avionics group described the fix as teaching the software to distrust itself. That's not a phrase engineers reach for casually. 6 minutes without trusted data. No second opinion from the ground. No comparison data set to pull up. The crew reads gauges that may be feeding them garbage and makes calls that won't wait. A guidance computer chasing bad numbers through superheated atmosphere isn't a glitch you recover from. It's how cascades begin. That takes us to number 7, guidance and navigation. Failure. Orion depends on star trackers and inertial measurement units to hold its angle through the atmosphere. Inside the plasma sheath, star trackers lose lock. Optical references go dark. The inertial system drifts, maybe a fraction of a degree, and the guidance computer is left stitching together fragments of increasingly unreliable information. At 25,000 miles per hour, a fraction of a degree is enormous. 1 degree too steep and the capsule digs in hard. Heating spikes. G-forces climb past what the models predicted. 1 degree too shallow and Orion skips back out of the atmosphere, or lands hundreds of miles from the recovery ships. The safe corridor is measured in tenths of a degree. To put that in perspective, commercial aircraft hold their glide slope to within a few degrees, and they've got radar altimeters, ILS beams, and a co-pilot backing them up. Orion has to be 10 times more precise at 30 times the speed, flying through plasma with degraded sensors and 0 ground contact. Victor Glover can hand fly for a stretch, using RCS thrusters to trim the attitude, but during the blackout he's doing it essentially blind with almost no room for error. JSC's entry flight dynamics team pre-programmed trim sequences and padded the pre-entry burns with extra margin to narrow the uncertainty window. Those measures help. They don't solve the underlying problem. When guidance goes bad, every backup system downstream absorbs a harder load. And the next item is the first system that takes that hit. Number 6. Reaction control thruster failure. Once the service module falls away, the crew capsule is on its own. 12 small hydrazine monopropellant thrusters arrayed around the capsule. That's it. That's all the attitude control Orion has left. Each one puts out roughly 160 pounds of thrust. Together they hold the heat shield pointed the right direction, counter aerodynamic torques, and execute the roll reversals that steer toward the landing zone. During the blackout, these thrusters fire on autopilot. Guidance algorithms command pulses based on inertial sensor data that may already be drifting from the problems in number 7. If a thruster valve sticks, or a fuel line develops a vapor lock under thermal stress, the system loses authority on one axis. The software can reroute commands to adjacent jets. It's designed for that. But every workaround burns propellant from a supply that doesn't get refilled. Hydrazine is finite. Every extra burst that compensates for a dead thruster is margin stolen from maneuvers that haven't happened yet. Data from Orion's EFT-1 test flight in 2014 showed propellant consumption came in below predictions, but that was a short, low-energy return from Earth orbit. Artemis II comes back from the Moon. Faster entry, longer controlled descent, tighter corridor. If the thrusters lose the fight during the blackout, the damage ripples through everything below this on the list. Guidance from number 7 gets worse. The tumble risk from number 4 escalates. The heat shield from number 3 starts taking load on surfaces it was never meant to handle. So 12 small thrusters firing on autopilot inside a cocoon of plasma are the only thing keeping the descent controlled. Number 5. Separation bolt failure. A single fastener sounds trivial until you picture it glowing inside 5,000-degree fire. After Artemis I, Post-flight inspectors found over 100 locations where the ablative material had chipped or fractured. Some of the bolts embedded in the heat shield had eroded or partially melted during reentry. Not catastrophically, but enough to raise questions that delayed the next flight by months. Those bolts anchor ablative blocks in place and hold critical structure together. If one softens under thermal load and shears, a chunk of avcoat breaks free at hypersonic speed. The hole it leaves behind does more than expose bare structure. It reshapes the local airflow. Heat concentrates on surfaces that were never designed to take direct thermal load. Wiring harnesses and bolt receptacles that should have stayed buried are suddenly exposed. By the way, this is the same failure principle that nearly destroyed Columbia in 2003. Not a bolt in that case, but the same physics. A small piece of protective material gone, and the airflow finds the weak spot immediately. NASA's response was methodical. Tighter bolt inspections, melt scenario simulations across multiple thermal profiles, trajectory adjustments to keep heating steadier and more predictable. The avcoat formulation itself didn't change. The blocks are the same chemistry that flew on Artemis I. What changed is how the vehicle meets the atmosphere, and that modification narrows the margin in other ways. A bolt failure at peak heating leaves almost no reaction time, and it never stays local. One missing fastener feeds directly into the next problem. Number 4, aerodynamic tumble. The capsule starts doing something it was never designed to do. An odd roll, a sideways shove against the harness straps, instruments jumping. At hypersonic speed, airflow that should peel smoothly across the capsule slams unevenly into a damaged patch or an altered surface shape. The asymmetry generates a twisting force, and Orion starts to rotate. Once it begins, tumble feeds on itself. The faster the spin, the less effective the RCS thrusters become at arresting it. Heating migrates from predictable zones to surfaces with no ablative margin. The crew feels the rotation in their stomachs before any gauge confirms it. A missing avcoat block from a bolt failure, a bad thruster pulse, an unexpected aerodynamic moment from an asymmetric char pattern. Any one of those can initiate the sequence. In 1969, the Soviet Zond 7 capsule entered Earth's atmosphere at lunar return speed and hit attitude oscillations that nearly became unrecoverable, and that was an unmanned vehicle with no lives on board. The physics hasn't changed. The speeds are identical. NASA treated tumble as a priority concern after Artemis I data came in. The entry profile was smoothed. Control laws were hardened, so the flight computer automatically counters asymmetric torques the instant they appear. Crews rehearsed upset recovery in the simulator until the correction was reflexive. Mike Serafin, NASA's Artemis mission manager, made clear publicly that tumble during the blackout was the scenario they spent the most simulation time on. A small upset can be arrested, a full tumble while the ground sits blind. That's what keeps entry flight directors up at night. Number 3, heat shield spallation. The protective layer on Orion's base is designed to burn, but in a controlled way. Char forms on the surface and carries heat away as it ablates. The shield itself is a single titanium truss covered in 186 blocks of avcoat, a silica fiber material mixed with epoxy resin. On Artemis I, the avcoat did something nobody expected. Patches of char popped loose and left over 100 pockmarks scattered across the shield surface. The root cause turned out to be trapped gas. Certain blocks didn't have enough porosity to let pyrolysis gases vent outward, so pressure built underneath the char layer and fractured it as temperatures cycled during the skip maneuver. If a full block separates at peak heating, the titanium structure underneath faces temperatures above 4,800 degrees Fahrenheit. With nothing between it and the plasma, there's no backup shell. There's no EVA option to go patch it at Mach 25. Mission planners made a calculated decision. Rather than redesign the AVCOAT formulation on a compressed timeline, they changed the entire return trajectory. The modified path shortens the worst heating window and holds the ablative in a steadier burn, so trapped gas vents continuously instead of building pressure. The physics is still brutal, and the models still carry uncertainty. Howard Hu, who managed the Orion program through the heat shield investigation, and acknowledged publicly that flying the same material into a different trajectory was a deliberate trade they had to make. Wiseman and his crew won't be able to see the bottom of their spacecraft. Sensors measure temperature and strain, but that's not the same as looking at it. A vibration that changes character, a shift in the low-frequency rumble, one instrument reading that wanders off the predicted curve. Those are the only clues they'll get. Number 2. G-force spike and ballistic entry. The nominal plan has the crew descending at roughly 4 Gs. Uncomfortable, but a trained crew handles it. The danger lives in what happens if the guidance system from number 7 fails during the blackout. Without a functioning lift vector, Orion defaults to a ballistic trajectory. Steeper, faster, trading precision for raw atmospheric drag. Zadai, G-forces spike to 7, maybe 7.5, within seconds. At 4 Gs, breathing requires conscious effort. At 7, blood drains from your head, your peripheral vision collapses into a gray tunnel, and your arms might as well be bolted to the armrests. Trained pilots can maintain consciousness with aggressive diaphragmatic breathing, but the line between functional and blacked out is measured in heartbeats. And remember, this crew has been weightless for 10 days. Their cardiovascular systems have already started to decondition. NASA's compression garments help push blood back toward the head, but they only partially compensate for the violence of a ballistic spike after days of zero gravity. The Soyuz TMA-11 incident in 2008 showed exactly what this looks like in practice. A guidance malfunction sent the capsule into a ballistic descent. The crew hit over 8 Gs. Soyuz commander Yuri Malenchenko reported tunnel vision and near blackout, and the capsule landed 400 kilometers from the planned recovery zone. It took hours for ground teams to reach them. A crew member who loses consciousness for 5 seconds, just 5, won't call out a warning, won't reach a manual override, won't help the person strapped in beside them. Orion is engineered to survive a ballistic entry. The heat shield handles the extra thermal load. The seats are rated well beyond 7 Gs. But there's a difference between surviving something and being able to function through it. A capsule that splashes down with an unconscious crew is a capsule nobody can assist until recovery helicopters reach the landing point. The gap between the vehicle making it and the humans inside still being able to act is what makes this entry unforgiving. Number 1. Skip entry trajectory failure. Orion doesn't fall through the atmosphere like a stone. It flies a skip entry. The capsule dips into the upper atmosphere at roughly 25,000 miles per hour, uses aerodynamic lift to bleed speed, briefly climbs back above the sensible atmosphere to radiate excess heat, then commits to a final descent. Elegant on paper. In practice, the margin is a knife edge. The flight path angle at atmospheric interface has to be held within less than 1 degree. Too steep and Orion digs in. Heating spikes past predictions. The ablative burns faster than designed. G-forces slam toward structural limits. Too shallow and Orion skips too high, overshooting the landing corridor by hundreds of miles. In the worst case, the capsule grazes off the atmosphere and arcs back into space on a trajectory the remaining propellant won't correct. No runway to circle back to. No go around. After Artemis I, the investigation found that the original full-duration skip let too much heat soak into the AVCOAT between heating pulses, causing the trapped gas fractures that cracked the shield. For Artemis II, engineers shortened the skip to a steeper lofted profile that keeps the char layer in a steady, controlled burn. The fix solved the gas buildup, It also narrowed the already thin trajectory corridor and cut the vehicle's ability to fly long distances downrange to dodge bad weather at the primary splashdown zone. One problem fixed, another margin spent. During the blackout, the crew won't receive updated trajectory commands from Houston. The flight computer executes the skip maneuver alone, reading degraded sensors through superheated ionized gas while holding a fraction of a degree corridor at hypersonic speed. If the angle drifts outside that corridor, there is no second attempt. No abort mode. The atmosphere makes the final call. One maneuver, flown blind. The last gate between the Moon and the Pacific.